Pleasure to be here at this interesting event. This is Boston, where I come from. It's not windy, as you can tell. The sun isn't shining and the city's brightly lit. Our mission, of course, is to allow this to happen without burning fossil fuels. I'm not a chemist, but I work with two terrific chemists, Roy Gordon, experimental chemist, and Alan Aspudaguzik, theoretical chemist. Their contributions will become apparent in what I'm going to tell you today. I'm going to start with some description of some technical aspects and some economic aspects of storage on the grid. I really don't need to introduce flow batteries because Vic Brushett did such a good job this morning. Thanks, Vic, you saved me some time. Aqueous soluble organics, we've introduced them into flow batteries. I'll show you where we are in performance. I also don't need to tell you this, but I'll reiterate the cost of wind and solar electricity have dropped so much that the greatest challenge to getting virtually all our electricity from these renewable energy sources is their intermittency, because the city demands something that looks like this, right? And nature gives you that something that looks like this or looks like that. So if you could have safe, cost-effective storage at scale, you could map this or that into that, and that would be one way of solving this problem. The issue about storage is the two most important figures of merit are the energy a storage system can hold in megawatt hours and the power in megawatts, and they come together in different proportions for different applications. And for this application, you need extreme proportions of megawatt hours to megawatts. That's the discharge duration at your rated power before your system is drained. And if you were to run overnight on your solar energy or through half a week between windy fronts, you can see that large discharge durations are needed. And that's the value proposition for the flow battery, because as Vic showed, you have the power conversion unit sized with your electrodes and membranes for whatever power you need. But if you want high energy to power ratios, you're just talking about big, dumb tanks, if the electrolytes are cheap enough. And again, Vic showed a quantitative plot. This is my imaginary rendition of costs. He had a log-log scale. I've got linear scales, but the cost of flow batteries can go down at long energy to power ratios, and that can cut under the cost of stacking up banks and banks of solid electrode batteries. So that's the promise of this design. I worked with Bill Hogan, who's at the Harvard Kennedy School of Government, to address the question, how cheap does storage have to be for arbitrage? Bill's the world's foremost electricity markets expert, so we looked at organized electricity markets. The PJM market is the biggest organized electricity market in the US. You can get complete hourly data over this 7-year period. We looked at all the prices on all the nodes, all the hours. There's two markets. There's a day-ahead market where you know the price is 24 hours in advance, so it's easy to figure out how to charge and discharge your battery to buy low and sell high and optimize your revenue. And then there's the real-time market where you have to guess, and of course, how well you guess, how good your machine learning algorithms might be or whatever. That ends up allowing you to use a more expensive system if you can play in this market. But let's just take an example. Say a 4-hour duration storage system. This plot says that all the nodes over this 7-year period, if your system cost was $150 a kilowatt hour installed, then it would have been profitable at 1/4 of the nodes and unprofitable at 3/4. If your cost was $125 a kilowatt hour, you would have been profitable at half the nodes, and if it was $100 a kilowatt hour, you'd have been profitable at all the nodes. So that gives you a sense of where you need to break even. In the real-time market, if you can program correctly, then you can raise the costs that are still tolerable, so 50% are profitable at $200 a kilowatt hour. But as the energy to power ratio goes up, the break-even cost goes down, and that's because there are fewer and fewer opportunities to charge and then discharge over these long durations where you don't have a chance in between in order to charge. So this is all a price-taking model. If this stuff went into the grid, it would change the prices, and we didn't actually try to predict this. This is just for a price-taking device. So the flow battery curve has to fall under this curve at least at some point if it's going to be used for arbitrage, which is the huge application on the grid. There are certainly other niches where higher cost systems would be favorable, and those places you'd be starting now. The most commercially advanced flow battery chemistry is the vanadium redox. That's shown here, storing energy in different charge states of vanadium and sulfuric acid. Here's one installed by Sumitomo Electric some years ago, 5 megawatt hours. There's the energy storage tanks. There's the vanadium, there's vanadiums in there. These are the power conversion units. It's worth noting that now Rongke Power near Dalian, China is building the world's largest battery of any sort. It's over 500 times this size and capacity, and 3.2 gigawatt hour vanadium redox battery. So that's pretty impressive. Okay. The problem with vanadium is it's a relatively rare and expensive metal, and its price is subject to fluctuations. There's not a whole lot of control over that. If you're aiming for a system that's $150 a kilowatt hour, something like that, and your vanadium costs $200, then of course you're screwed. Okay. So we've been looking at organics that can be a lot less expensive than that and possibly can approach the performance of vanadium. And the one that's worked best for us is this quinone. So I'll start here with a benzene ring. There's protons on those corners, hydroxys here, and at the right potential in aqueous solution, that will give off 2 protons and 2 electrons and turn into that oxidized form there. And it can go back and forth between them pretty reversibly. We'd been looking at inorganic ways of storing energy, like a lot of people, and noticed that groups were making progress using organics in fuel cells, and thought maybe we can find organics that work in two-way operation for a flow battery. I started talking with chemists Roy Gordon, Ted Betley, Alana Spuduguzik, and we hit upon this quinone that's in photosystem 2, where it picks up electrons from chlorophyll and goes back and forth between oxidized and reduced forms over and over again. That's what you want to happen in a battery. The potential wasn't right, of course, but there are ways to change the potential. The solubility was low, but there are ways to change the solubility, and so this is the course we took off on about 5 years ago, looking for high-performance organics that would be soluble in aqueous media. The idea there is that maybe we can push this cost curve down into really low numbers here and drop down below solid electrode batteries even sooner, and maybe down below the grid requirements as well. So the vision is to try to make aqueous batteries, aqueous so that we don't have fire risk, organic so the chemicals can be cheap, and we'd have different molecules with different reduction potentials on the two sides. We can have different functionalizations here that will make that happen, and maybe if we can oxidize this hydroquinone here to that, protons can go through a cation conducting membrane, electrons through the outside, and reduce that one. That would be a charging, and just reverse those in discharge. As we've been looking at chemicals we can either purchase or synthesize, the way we've screened is primarily for reduction potential. We want as wide a difference in redox potential as possible between the positive and negative sides without splitting water or having other unwanted side reactions. The solubility has to be high to give you a reasonable energy density. The kinetics have to be reasonably fast to give you a reasonable power density. The chemical stability has to be high to give you a reasonable lifetime, capacity retention rate, and then the mass production cost has to be low, at least at large scale. This is the first one that worked for us. We published 4 years ago. Anthraquinone disulfonate, there it is in the oxidized form. The energized form is the hydroquinone you see there, and so this is in half of a flow battery. The other side was a conventional inorganic side that we'd had previous experience with, bromine hydrobromic acid. So this, we push it through a porous electrode. Here it is, it's just a carbon paper. Redox happens on the carbon fibers, and we release electrons to the fibers and protons to the electrolyte, which go through this Nafion membrane. It's a fluoropolymer, conducts protons. That comes over here and reduces the bromine to hydrobromic acid. And so here's one of the first cells we had, and it worked really pretty well. This is what's called a polarization curve for the flow battery community. You can draw a current density and ask what the cell potential is. So at open circuit here, you're at about 0.8 volts of open circuit potential. It changes a little with state of charge, as you can see. And the slope of this is proportional to the internal resistance of the cell. So you want low internal resistance to get low slopes. You saw this plot from Socina, a power density versus current density. Just take the same data, multiply the voltage by the current density, and you get power density. And if you can only carry one number around in your head when you're comparing systems, we carry peak power density around. So here we can get to a watt per square centimeter, which is a pretty good number. It's in the same ballpark as vanadium. I forgot to look this up, but the highest vanadium published value, I think, is around 2.3. So we're in the ballpark of vanadium. Vanadium's been around for a quarter century, and this took just a couple of years, and we think there's still room for improvement. You can take the same data and say, okay, I'm not going to run at the peak power density because that's low efficiency. What efficiency do I want? Suppose you want 80% round-trip efficiency. Then you might have a spec where you plot, you go to 90% efficiency in charging and 90% efficiency in discharging, and this tells you what power density you could do that at. You say, with this system, you could get there at between 1/4 and 1/3 of a watt per square centimeter, which is still pretty good. This is the best power density of any of our chemistries. It has problems that I'll tell you about sooner or later. But what I want to point out here is that there's this trade-off between voltage efficiency and power density, because you can drive things to higher power density. You want to do that because if you can double your power density without changing anything, you've just cut your cost of power in half, right? Your cost per kilowatt in half. But then you lose efficiency. And so understanding what leads to these internal resistances and keeps these curves from being more horizontal and allowing you to get out to enormous power densities is one challenge we're working on now. Another challenge is understanding the production cost of these things, because when you have low volume chemicals or when you produce the first of any chemical in the world, it's hard to know what the cost is going to be, and the cost has to be low. Our first two chemistries were here. I showed you this one. This one's base soluble. It's very similar, and this was under an ARPA-E program where we had a consultant who'd recently retired from the chemical industry do a study based on the synthesis that Roy Gordon's lab had produced, temperatures, times, concentrations, and so on, and estimate what the cost would be as a function of scale. And I think of this as, if you're about 1 volt, then a kiloamp hour is a kilowatt hour. Right? So I think of this scale as dollars per kilowatt hour, and this is megawatt hours per year. And you can see at small scale, the cost is really quite high. But when you get out to the scale of 1 Ronca power mega battery per year, the cost is close to that of the raw materials, which is, in this case, below $20 a kilowatt hour. So that's really encouraging, but you have to get there. So imagine talking to someone about financing a startup company that's going to start here. Right? It's just a very hard thing to do. Back to the efficiency loss problem. We're looking into the guts of electrodes now and trying to understand where the losses come from. This was a study we published last year on some of the voltage losses. So we split up a porous electrode. There's a membrane here, there's a current collector here, and just some inert voltage probes in here to see where the voltage drops were. From that, we could deduce where the losses were, and this is a plot of overvoltage versus current density. So this more voltage, overvoltage is more loss here, and the slope is a resistance or an area-specific resistance in this case. And we could back out the contributions from the membrane, positive electrolyte, and the quinone-bearing negative electrolyte. That's that whole thing there. So that's the single biggest source of voltage loss in this system shown there. We could actually break it up into the Faradaic charge transfer reaction, ionic conduction in the liquid electrolyte, and electron conduction in the solid as well. But we're now looking more deeply into that by developing visualization techniques of what's going on inside the porous electrodes at sub-pore scale. So here's our flow battery with 2 centimeter flow field, and you saw this as well from Fix. So you have a high pressure inlet, it's interdigitated. The only way to get to the low pressure exit is to be forced out of the plane of the page into this porous electrode, flow across the rib and down. And inside the electrode, you have these carbon fibers, typical 10 micron diameter and maybe 50 micron pore size there. And there's a bunch of commercial porous carbon papers, and they all look different. Does it matter? Well, you can measure polarization curves, and that's a rather crude way of asking, what does it matter? Another thing that we've learned to do is optically image inside these electrodes and see what's going on, because these quinones fluoresce, and they fluoresce at different wavelengths in their oxidized and reduced states. So we can peer in, so we'll peer into this area here between an inlet channel on the left and an exit channel on the right as electrolyte full of quinones moves from left to right, and we're providing protons through a membrane to reduce them. And I think I only have time to show you this movie here. So here we're just flowing oxidized quinone. Right, it's all oxidized, it's coming in oxidized, there's no electrochemistry. And then we turn on the current, and we can watch the reduction, where it happens. And we can see fast flow paths, and we can see what look like stagnant paths, and we can see reduced stuff coming out here now. And this scale of about 2 millimeters is enormous compared to the typical pore size, which I have over there. And the scale of the inhomogeneity goes across the entire rib. And this is a characteristic commercial interdigitated flow field rib size. This is not just lab scale. Those ribs are about that size. And these inhomogeneities matter to an unknown extent at this point. Okay. When we take snapshots in 5 different commercial electrodes, they all look different. There's what Newman porous electrode theory told us to expect, and that's what went into our early models. And this is what's actually going on. And so we're going all the way from the inlet channel to the exit channel in each of those cases. And what do you want your electrode to look like? Okay. We're not sure at this point. Okay. In the same experiment, we can image the velocity fields, the flow field, because we can put in fluorescent tracer particles that fluoresce at yet a different wavelength. Whoops. If this video is willing to play for me. So you can track these particles as well and see what the velocity field is. And you can take strobes of those and map out the whole thing. And so in the same piece of electrode, you can image the concentration fields and the velocity fields as they evolve in real time, and we can get to sub-pore resolution now. So I'm really excited about our opportunity here to understand what's going on at a sub-pore level within these electrodes and use the understanding to design structures that will give us better performance and much less voltage loss for the same power density, let's say. The third challenge, and maybe the hardest, is lifetime of these organics. And we didn't realize this till about the past year. This is one, we didn't develop this one. This was from PNNL, but it was interesting to us, so we started studying it. It operates in neutral pH, and it picks up and gives off 1 electron typically, unless you do something extraordinary to it. And we started looking at cycling experiments. Our flavor of the cycling experiments that Fix showed is we have one side that's smaller, that's the capacity limiting side, but it's completely symmetric in composition. So open circuit voltage is 0, but now we fully cycle this and we know we can study the fade, and sometimes it depends on state of charge, and that's why having one side be the capacity limiting side makes a difference. And here we're cycling over 3 days, just methyl viologen against itself. A pretty good-looking fade rate per cycle, extrapolates to 20% loss after 1,000 cycles. That's really reasonable. But in that middle day, we weren't cycling. It was just sitting. In all of the organics that we've looked at carefully enough to tell the difference between cycle-denominated fade and calendar-denominated fade, the fade is entirely calendar denominated in all of them. And that caught us by surprise. We had learned from the solid electrode battery community to just cycle the hell out of these and count the cycles. But no, you got to count the days, and that takes a lot longer. All right. Well, if you know something, if you can learn something about the decomposition mechanism, then you can do something about that. In this case, Eugene Bay, a postdoc working in our group, was able to infer that there was a bimolecular decomposition mechanism here, and he added some positive functional groups to turn this thing into a tetracation, the hypothesis that Coulomb repulsion would now keep them from touching each other, and it worked. Right? So this now is, we call it bitmap biology, and there's the acronym, and it just is rock solid. If you extrapolate that to a fade per cycle or a fade per year, that looks acceptable now, and I'll talk about that more in a minute. The problem with this chemistry, the reason why it's not, we're not going forward with it, is the full cell. On the positive side, we put the same functionalization on a ferrocene, open circuit voltage of only about 0.7 volts. And as you heard from Fick, low voltage raises your cost. So this seems to penalize it. Also, this is near neutral pH. It's an anion conducting membrane. They tend to have higher resistances than the cation conducting membrane, so that hurts as well. But it's a proof of principle that you can stabilize those molecules. And they don't have to have infinite lifetime in order to compete with, say, vanadium, because you can trade off the future, the replacement cost, take the present value of the future replacement costs, discounted by whatever your preferred interest rate for discounting is, and trade that off against the capital cost savings here, and I call that the replacement cost ratio, and figure out when that's going to break even based on the relative cost of your organic and vanadium. So for example, if vanadium costs 100 units and the organic costs 30% of that but loses 15% per year, then the replacement cost ratio is 15% of the 30 units over the savings, which is 70 units, and that's 0.064. So if you have a 20-year project, that breaks even at a 2.3% interest rate for discounting. If you say, well, my vanadium lasts forever, so I'm going to reuse it in the next battery, then that's equivalent to having an infinite life project, and then your interest rate for discounting where it breaks even is here. So if your chemical cost is high as a fraction of vanadium, it's going to favor vanadium. If it's low and your interest rate for discounting is high, it's going to favor the organic. And of course, this assumes that there's no additional reconditioning cost that would have to go in there. You may have to put that into an actual model when you have actual costs. So here's our newest chemistry, where we've also managed to protect molecules that used to fall apart. We call it Methuselah-quinone. For those of you who are not familiar, Methuselah was the longest-lived character in the Bible. And we took that dihydroxyanthraquinone and put these groups on, functionality, and they suppress a decomposition mechanism that we haven't quite published yet. But we call it, Debeek for shorter than Methuselah. Debeek against itself, and just cycle this one. And it looks really quite good. So this is a very low capacity fade now. We just published this in Joule this summer, so I'm really excited about it. It seems like maybe now we have a viable chemistry. In the full cell against ferrocyanide, we've got a little over a volt of open circuit potential. It operates at pH 12 to 14. At pH 12, you have less aggressive chemistry. We can use non-fluorinated membranes. This is a commercial membrane that should cost less than an order of magnitude of the cost of fluoropolymers at scale. That's fully framed and ready to put into your stack according to the manufacturer. Here's the polarization curve. So we've got a little over a volt of open circuit. We've got very linear kinetics here out to hundreds of milliamps per square centimeter and a peak power density of maybe a quarter of what we had for the AQDS bromine system. So we think we can still improve on this, but the first thing we need to improve on is the full cell. So if you put this against ferrocyanide, we quadruple the fade rate. And we don't understand the mechanism of that at this point. We go back here to this fade rate. This proves the lifetime of the molecules, all right? This is a more complicated system, and we're looking into what the cause of the quadrupling of fade rate is. We think that there's some diffusion of the active species across the membrane, even though ex situ measurements say the diffusion rate is negligible. In situ in an operating cell, we don't know yet. So we're working on that. These are the important data. Ignore those. I don't have time to tell you about those. Okay. So let me just summarize and say, what I see in challenges here are this efficiency-power trade-off. We'd love to have, very high power density to bring down our cost per kilowatt, but when you do, you lose efficiency. Understanding what's going on inside the electrodes is an avenue to winning that war, I think. Lifetime and voltage is an important trade-off as well. Let me show you an example here. So I put up some other chemistries as well as ours here. And let's look at the neutral pH. So there's bitmap viologen, bitmap ferrocene. That's our chemistry, 0.7 volts, stable. Okay. You can have other viologens, but all the viologens that we are aware of with lower reduction potential don't have sufficient lifetime. There are other functionalizations of ferrocene, insufficient lifetime. So is there a fundamental trade-off between voltage and lifetime that's going to limit us? I'm not sure in these molecules. Here in acid, there's AQDS, our first chemistry, not stable enough. There's no high potential molecule there. In base, DHAQ, our first soluble in base, unstable. That's there. Bring the potential up a little bit to Debique, and now we have adequate stability here. No organic here, but this one seems to work pretty well. So this is an important trade-off that we haven't really, don't have answers for at this point. And finally, mass production costs. We know that that one's really cheap and that one's really cheap. We just don't know at this stage about that. So we're left wondering. Okay, so I'll wrap up. Here's a table, just the chemistries we've introduced. I have other slides with other chemistries as well, but none of them have adequate lifetime, okay, except for this one and that one. So this is the bitmap neutral pH bitmap viologen, bitmap ferrocene with adequate lifetime. In fact, the longest calendar life of any flow battery ever published. Extrapolated, of course, but low voltage. And here's our new Methuselah chemistry with now adequate voltage, adequate calendar life. If we can understand the difference between the symmetric cell, very low capacity fade, and the full cell, which I think we should be able to do. But we don't, so I think that this may have pass all the technical requirements. We don't know about the production cost yet, and that could kill it or it could be okay. So I'll wrap up by pointing out my collaborators here. Roy Gordon in charge of the synthetic chemistry, Alana Sputuguzik, whose combinatorial theoretical team has calculated the properties of over 1 million different molecules for us. The Methuselah cell is the work of Kai-Shang Lin and David Kwabi. And the bitmap reagents, bitmap viologen, bitmap ferrocene was a work primarily of Eugene Bay. And I'll thank our financial sources of financial support and be happy to answer questions if this time. If not, we'll go into the later afternoon session.